Hi, this is my lab for bar magnet presentation. So, introduction. The purpose of this lab was to mathematically and kinds of physically relate how distance and strength of a magnetic field change, as well as understand how different orientations can affect said field. We were also able to make a computational model of what we found and relate it to numerous equations. So some physics concepts and equations we needed to know was the Biot-Savart law, the magnetic field of a dipole, and the distance-dependent formula of a bar magnet. So the physical experiment, the first one we did, is we first had to locate the exact position of the magnetometer. We then had to orient this phone to negate or not take into account Earth's magnetic field. Because we are only moving it along one axis, we essentially put the Earth's magnetic field perpendicular to that, and then we measured various distances between the bar magnet and magnetometer depending on what the value read on the magnetometer, and we recorded these distances in this spreadsheet for around each value of microteslas. All of the distances we found were incredibly similar, which means our data was extremely precise. And with this information, we managed to get an equation. An equation for a line. Now, this is very important because we can use this equation to find mu, which is the magnetic dipole moment of the bar magnet. So we can use the slope because we know it's the n value in this equation, and then we can use the slope because we know that it's equal to ln k, and we can then solve for k in this equation. So knowing those two parts, we know this is an equation which we can rearrange to solve for the mu, which is the magnetic dipole moment. And now, as you can see, the only unknowns we really have can be solved by using these parts of that equation. I forgot to replace the n here, but it is equal to this value. We can assume that r is around 1 meter. And with that, we get that our mu, or magnetic dipole moment, is equal to 1.56 amperes times meter squared. So then our off-axis is where we first had to find, we moved essentially on both axes. So we first had to find the distance horizontally, where it was around 100 microteslas. We then used this distance, we placed it that same exact distance upwards, which means we essentially have a right triangle where we know this angle here. So that allowed us to solve for d. Next, we essentially had to everything else we were able to just read off the magnetometer, like the x and z components, but the y component we had to essentially take into account that Earth is affecting our values here, so that is what by corrected is, and with that we can solve for b net, which is 2.84 times 10 to the negative fourth. So this is what we found physically. Now our computation you will find familiar is what we calculated earlier. This dipole function moment, this dipole moment function is just the equation put into code. And then all of this code here, all it's doing is this part is just creating essentially observation points. And then all of these numbers here, there should be a fourth one here. You'll see it on the computational model. But all it's doing is that it's creating a magnitude. It's taking that dipole function and it's applying it to that observation point and that magnet. And so it is essentially creating magnitudes for the arrows. Same here, except it's creating the magnitude for this 45-degree arrow, which is going to be extremely important. We will use that to find our b net. So as you can see, all of our arrows here, the magnitudes are kind of differing. Obviously, closer to the magnet, it is stronger. So what's important here is that this is our x and y component, right? So we can use the Pythagorean theorem to get our value of 1.28 times 10 to the negative fifth. We did find that our physical experimental value was not that similar, but it could have been due to some possible errors. Like, the magnetometer was it would fluctuate a lot, and we could have accidentally tilted the phone slightly, we didn't take into account Earth's magnetic field properly, and so that takes us to assumptions where we assume that this was a perfect dipole, and we assumed we perfectly negated the effects of Earth's magnetic field. So some conclusions and what-ifs. We needed to orient accounting for the Earth's magnetic field because it could have added more magnetic field, meaning we could have not given us an accurate representation of the value that the bar magnet was actually adding to our b net. So another question we had is if we put two magnets side by side, what would change? is essentially putting two magnets together. All that does is create one big magnet. So the direction wouldn't change much, or actually the direction wouldn't change at all, but what would change is the magnitude, because you've essentially created one big giant magnet. So yeah, that is the end of that. Thank you so much.